All right, guys, we're going to pick up where we left off in the last class. We're still doing our DMVPN configuration. Our objective today, of course, is to kind of get through the rest of the configuration because we've done all of the hub and the spoke configurations for our DMVPN configuration. We need to convert this to DMVPN Phase 1, which means getting rid of the multi-point interfaces on the spoke routers, which we'll do a little bit later on. But we still also want to take a look at some of the packet captures and maybe start to analyze what's going on with the NHRP protocol in this topology. And that's where we're going to pick up from based on what we discussed the last time. So just to kind of go back through the process here, router 5 is our NHRP server, next-top server. The spokes are router 1, router 2, and router 3. Let's just go ahead and verify that we have from our previous discussion, show IP, or let's do show DMVPN first. Yep, all the tunnels are up. Show IP NHRP. And we should have the resolution for each of the NBMA destinations. So 10.10.10.1 is router 1, 10.10.10.2 is router 2, and 10.10.10.3 is router 3. What I'm going to do, though, in the process of kind of identifying some of the packets that are going back and forth between these endpoints and the encapsulation, I'll shut down a couple of interfaces, and then we will capture information about DMVPN. As we had talked about in our last lesson, this is a tunnel that supports multicast traffic, but it is a unicast tunnel. And that's why we had that multicast mapping that we specified, because we wanted to make sure that we're sending the multicast traffic over that unicast tunnel as encapsulated data. We're going to add RIP to this topology later on in our lesson so we can see how those RIP datagrams are going to be encapsulated inside of those unicast packets, even though they are, in fact, multicast packets. All right. So the DMVPN Phase 1 routers, these are going to run as point-to-point routers. So let's go ahead and go into router 1 and do a show run interface tunnel 0 and take a look at the difference between what is a multi-point configuration, which would be essentially DMVPN Phase 2, and what is a point-to-point configuration. We can see here that we've mapped the VPN address 10.10.10.5 over to our NBMA address 209.165.200.245, but we've specified the tunnel mode as multi-point. So that's the first thing that we're going to do, is to convert this to DMVPN Phase 1, which will not allow spoke-to-spoke communication. I'm going to go into interface tunnel 0, and I'm going to say no tunnel mode GRE multipoint, and I'm just going to simply say tunnel mode GRE. So that's one of our options. We can do GRE over IP, or we can do GRE over IPv6. Our underlay network is IP. So that's what we're going to specify our tunnel mode as. Now, if I do a show run, interface tunnel 0, I can see that that command actually doesn't show up because that is the default, right? When you're setting up a GRE tunnel, that's the default. The next thing that we need to do is we need to specify the tunnel destination. The tunnel destination needs to be specified when you're not using a dynamic multi-point GRE interface. So I'm going to come in here and say tunnel destination, which is going to be the NBMA address, is going to be 209.165.200.245. Show DMVPN. So the tunnel is up. Show IP NHRP. And we've registered with the tunnel. So the tunnel was created 57 seconds ago. All right. That's really the only difference between Phase 1 and the other phases as far as the configuration goes. Phase 1, Phase 2, and Phase 3. There is a couple of other things that we would have to do for Phase 3 operations. We'll take a look at that when we get into our lesson on DMVPN Phase 3. So let's go ahead and do the other conversions on router 2 and router 3. Interface TU0, no. let's just do a show run interface TU0. And let's do no tunnel mode GRE multipoint. I think we should just be able to do tunnel mode GRE IP and tunnel destination 209.165.200.245. All right, same thing on this guy as well. Interface TU0. Let's copy it from here. All right. And copy it from here. Now, as far as what's configured on the hub, configuration doesn't change on the hub. We still have a multi-point interface on the hub that allows us to establish the tunnel communication, the VPN communication to the spokes. Okay. All right. And remember, we did that. We allow that multicast traffic over the tunnel because we defined the multicast map on the spoke to the hub router. That would still be something that we would have to do regardless of the phase if we want to be able to run dynamic routing protocols and other types of protocols over the tunnel. All right. The tunnel destination is never specified in our multi-point interfaces, but like I said, with DMVPN Phase 1, we do specify the tunnel destination, and that's really the only significant difference between DMVPN Phase 1 and Phase 2 with regard to the configuration. All right. So we've applied the configuration. Now we're going to go ahead and do some Wireshark captures so that we can take a look at some of the different NHRP messages that are going back and forth between these different routers. Now, we did talk about this a couple of videos ago when we did our initial DMVPN introduction. Let's go ahead and capture. Let's make sure that when you are doing the packet captures, that you're capturing, and this may be a challenge. I think I should be able to do it, but typically you want to capture on the underlay interface. And unfortunately with GNS3, I didn't even think about this, we would be capturing on the physical interface. I think that should be okay. Yeah, that's exactly what we want to capture. We want to capture on the underlay interface anyway, because at that point the encapsulation has already taken place. And since we're not running encryption, it's not a big deal because we can still see the data that's being captured. All right, so let me go ahead and take a look at, like what we did the last time, take a look at just the basic ICMP messages going back and forth or other packets that are being encapsulated. So we'll start our packet capture on router 5. Then I'm going to shut down a couple of the interfaces. Actually, I've already just shut down the one on router 1 so that we can see the NHRP messages going back and forth as well. We'll talk a little bit about what those messages look like, what are some of the elements of that configuration, and see if we're getting any, well, we'll see all the details, of course, of the different NHRP messages. So let me go ahead and do some generate some packets here. Ping 192.168.50.1. That should be the loopback interface on router 5. Let me do a show IP interface brief. We're not doing routing yet. So I'm just going to have to ping the tunnel interfaces for now. Let's just ping 10.10.10.5 and just generate a few pings here. Because we're not doing any of the routing, we haven't added our overlay routing yet, we're not going to be able to reach those loopbacks. That's kind of the whole point, right? Is to be able to route between those different network segments. All right. So if we look at the layer 3 encapsulation, as always, this is just a standard packet header. But you'll notice that we're using the NBMA addresses as the source and the destination, 200.241 as the source, and 200.245 as the destination. Nothing really particularly special about this packet, right? We see no DSCP is applied. It's kind of a standard packet header, 20 bytes or IP header. It's got a time to live of 255, but we're specifying that this data is encapsulated inside of a GRE packet or a GRE payload. And that's where we see protocol 47. Other than that, though, it's pretty much a standard packet capture. If I look at the GRE header, we see some very basic concepts here. The flags, we'll get into some of these flags a little bit more. And we did do a GRE video way back in the beginning of this course as well, where we talked a lot about different tunneling protocols and identified how those tunneling protocols worked. But in this case, we really only have one bit that's set, which is the key bit that allows us to identify the idea that we're establishing this tunnel using the key IDs and key material. We'll actually see the key material here. Now, if you recall, our key was what? I think it was 01. Let me see. Let me see what our key was real quick. We still have the configuration applied here. So, yeah, the key is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And I believe, if I'm not mistaken, so the key itself is being converted to hexadecimal format. We're utilizing a key of 1, 2, 3, 4, 5, 6, 7, 8, 9, which then converts over to hex 499602D2. So you can derive the key from the packet. That's why we don't really consider having a tunnel key, as an adequate means of security. So if somebody is able to capture these packets, they're obviously easily able to identify what the key is, right? So we still want to add our IPsec encryption, our authentication with IPsec as well, to provide that true security between the two endpoints, between the tunnel endpoints. All right, as far as the other captures go, we're seeing in this case pretty much just our 24-byte GRE header, and then we have our VPN packet here, which specifies a tunnel source and a tunnel destination, and that looks like a standard packet. So it has a protocol specification of whatever the payload is. Later on, we'll see that would be UDP. Because we're going to run RIP on top of this network, and we'll see how those UDP packets are encapsulated. All right, so that's fine. We can ping all the other tunnel interfaces, but what we want to see is what's happening on the back end to allow this communication to take place, right? What is it that allows the spokes to register to the hub, and what allows the hub to recognize those spokes, and so on. Typically, in the case of most modern DMVPN configurations, we specify the tunnel source, but we never specify the tunnel destination, because we do want that spoke-to-spoke communication to be able to take place, and we want to be able to manage that communication. But since we're running DMVPN Phase 1, in the case of the spoke routers, we don't have that. But it still doesn't really matter. We're still going to use NHRP to dynamically tell us when we're building the encapsulation, how to learn about those destinations. In the case of the hub, that's still going to be the case, because the spokes have to call home to the hub, and the hub has to then dynamically register those spokes. So let's see what an NHRP registration request looks like, how it's carried inside of GRE, and then we'll take a look at the actual payload inside GRE, which in this case is going to be NHRP. So I'm still doing my capture. Let's go ahead and shut down the gig 00 interface on the, we'll just use router 1 in this case. Interface gig 00. We'll shut that interface down. That should clear out the tunnel, right? If I do a show IP NHRP, the tunnel, well, there we go, tunnel went down. Show DMVPN, and I should see, yep. So it shows that well, on this particular case, it shows that the tunnel is still active, but eventually it will clear itself out. Let me just go ahead and go into tunnel 0 and shut that down as well, and do a no shut on tunnel 0. Okay. Now if I go to router 5, I should be able to see show IP NHRP. Similar output here. Notice here that the tunnels identify when they're going to expire. This guy's going to expire in 1 minute. Yeah, it's going to expire for. Let me do this. Clear DMVPN. I'm not sure if this is a session. Valid option. Interface gig 00. No, let me see. Tunnel 0. Show DMVPN. All right. Let me make sure I didn't clear out the entire config. It's still there. Oh, that's weird. We'll shut these guys down and get them restarted. See if they come back up. Yeah, so the problem with the GRE tunnels is they're on-demand circuits, right? Well, actually, the spoke-to-spoke connections are on-demand, so these are permanent. The spoke-to-hub connections are permanent. So as long as they're registered initially, GRE is going to think that those circuit paths are still available, and we'd have to use other mechanisms to verify whether or not the tunnel is active or not. So you kind of have to go through a process. Now none of my tunnels are registering here. Let me do a show IP interface brief to get those reset. 3. Yeah, so like I was saying, specifically for the spoke routers, you can reset the connection on the hub, but because the hub is not the router that's actually initiating the tunnel and establishing the tunnel communication, you have to kickstart the tunnel on the spoke routers. This would be very helpful, obviously, on the lab if you're running into a situation where you have to test and verify operations with DMVPN. Can't really do that from the hub. You have to initiate those connections from the spokes. All right. Show IP interface. Let me do show IP NHRP, and I should see 2. Yeah, router 2 and router 3. Now at this point, I've already started capturing a bunch of NHRP messages. That was the overall goal. I'm going to leave router 1 down for now, and we'll just focus on router 2 and router 3. But now let's go back to our Wireshark capture. And we should be able to identify, apply filter. Let me come in here and see if there's a way to filter this based on, well, let's just do apply a filter based on GRE. All right. So we can see now here that we've got all of our NHRP messages, and that's really what we want to go through is these registration request messages and the registration reply messages, so we can kind of break down what those look like. I had a question from a student at one point that said, hey, what is NHRP encapsulated inside of GRE, or is it just routed differently over the link between the MBMA addresses? Or are we using the actual VPN because it's kind of like a chicken or the egg type of scenario, right? We're trying to establish a VPN tunnel using VPN using messages that run over the VPN, right? It's kind of like, okay, what comes first? Do we have to establish the VPN and then create this tunnel and identify the spokes to the hub, or how do we do that, right? I mean, if you think about it, I'm not saying it very well, but if you think about it, what we're trying to do is we're trying to establish these registrations from the spoke to the hub. So it's a little bit counterintuitive to say that we're going to use the VPN, which we're to establish that, because the VPN is what we're actually trying to set up. But in fact, NHRP messages are encapsulated inside of GRE. We can actually take a look at this. Here's the first message here, right? This registration request. Now, clearly the source and destination are still going to be those NBMA addresses, because that's how we route traffic from one point to the other, period. All right. The mechanism, obviously, that we're using here to be able to establish these tunnels is NHRP. This is a client-server relationship, but the spokes acting as the client, or what we call the next hop clients, they need to register with the next hop server, and then it's up to the next hop server to track all of these different registrations. All right, so let's take a look at, from router, is this router? Yeah, router 2's perspective. How did this communication process take place? All right. If we take a look at the actual packet, the NHRP packets themselves are comprised of two different parts. All right. Normally, it's standard kind of normal layer 2 and layer 3 information, which we see as our Ethernet 2 header and then our IP header. And then we have our GRE tunnel, since NHRP actually runs through the GRE tunnel. And then right after that, we get our NHRP portion of the packet. RFC 2332 is what defines how NHRP is constructed. But we can kind of go through this and break it down a little bit, right? So here's the first, when I was saying that there are two parts to the packet. This is the first part, which is the header. And then we have the remaining information, which offers additional information about the packet. Now, we don't have to get into all of the details of each component of the NHRP registration request, but I do want to break down some of these pieces. So let's expand the NHRP header. This is always going to be the same regardless of the NHRP message type. It's basic information, like what is the NHRP version we're running, what are the ether types of the physical medium, what are the address, what's the address family information, and so on. So we're seeing that this is NHRP over IPv4, protocol hex 800, hop count is 255, that's based on the time to live, NHRP packet checksum, which was actually verified, NHRP version defined in RFC 2332. And then we identify the packet type. In this case, it's a registration request, which is type code 3. Now, this is where the important information is, right? Because this, as we get beyond this part, we're able to identify what the IP address information is. Remember, the overall goal of NHRP is to be able to map the NBMA address to the VPN address. And that's what our overall objective is. And that's what we're going to see here. In fact, that's going to be part of the mandatory part. So let's go ahead and close this piece up. And we'll go into the mandatory part. This is where the NHRP packet type is defined. Is this a registration request? Is it a reply? Is it a resolution request? Is it a resolution reply? What's the tunnel interface? That's going to be identified as the protocol address. So the protocol length is 4 bytes. The destination protocol length is 4 bytes, indicating that we're using an IP address. The protocol address is the VPN address, 10.10.10.2. That's the source VPN address. And then the destination protocol address is the destination VPN address. And then we also identify what our source NBMA address is, which is for the underlay network, okay? And that's where the physical interface address is applied. Basically, it's the IP address of the outside interface. All right. Like I said, we don't have to go through every piece. If you guys are really interested in seeing more about each of these components of the NHRP messages, take a look at the RFC. But again, not something that we're really too concerned about. It's not something you guys are going to have to know for the exam. All right. Now we do have these things called client information entries. That would contain specific information for the clients themselves, like what are my hold down timers, what are the MTUs, and so on. That's this piece right here, where we can see the MTU, the hold down timer, and some of these other fields that aren't set. These will change depending on the version of the DMVPN mode that we're using. Some of these fields are not used in DMVPN Phase 1. All right, so overall that's the NHRP registration request. Now what we want to do is we want to take a look at the reply. All right, so we can see that the client 10.10.10.2 is registering with 10.10.10.5. And we want to go take a look at what the reply looks like. It's pretty much going to look exactly the same. Well, not exactly the same. It'll be slightly different, right? So here's our reply. Let's see. Yeah, that's to router 2. All right. So as far as the packet encapsulation, it's pretty straightforward. We don't need to look at that piece. GRE is going to be pretty straightforward. Don't need to look at that piece other than this identifying as the payload is NHRP, which is type 2001. And our fixed header, pretty much going to be the same thing. Our transport is IPv4. This is the checksum. This is the version. But the type code is 4, which indicates that it is a registration reply. So as far as the fixed header goes, it's always going to be the same format, regardless of the different types of NHRP messages. There might be some slightly different values in the fields, but other than that, it's going to be just a standard format. All right, and then we can specify the MBMA address. That's the source, which is interesting that is identified as, oh, yeah, this is not the actual registration reply from the hub. Well, that's interesting. It does say it's coming from 245 and it's going to 242. Yeah, I'm not sure why it's specifying the source because this packet is coming from, well, in this case, yeah, this is 242 to 245. But let's take a look at the reply here. So it's 245 to 242. So that's router 5 to router 2. And what I would have expected to see in the NHRP registration reply was the source MBMA address as 245. But, this is encapsulated information. So it's probably in relation to the request that was sent. We're identifying the registration reply saying you're registered. And we're specifying the original source based on that information. Let's see, we have anything else here to indicate that the registration is accepted. We might have to dig into the RFC to kind of find out why that's specifying in the reply that the source is the client as opposed to the server. But in any event, I'll see if I can take a look at that before we get into one of our other discussions in the future about NHRP. But in any event, the fixed header, not much to see in the fixed header, right? Basically includes all the same information except for maybe the type code is a little bit different. That's about the only difference. But as far as the actual format of the fixed header, it never changes regardless of whatever NHRP packet type is sent. Protocol, address family, and so on. That's pretty much what you're going to see. It's the mandatory part of the header that actually defines the NHRP packet type. We already looked at the resolution request that was sent from router 2 to router 5, and so on. There is one thing that I want to clarify in this discussion, though, and I think we've already kind of clarified that, even though I kind of misspoke in the last lesson about the difference between the DMVPN address and the VPN address and the NBMA address. But we do have a lot of addresses that show up in this section, the mandatory part. The source NBMA address is the IP address of the physical interface. I just want to make that clear. And then so is, the source protocol address is the actual address of the DMVPN tunnel on the client. The destination protocol address is the IP address of the DMVPN tunnel on the other side that the client is trying to reach. Okay, so MBMA addresses are for physical interfaces with regard to the capture here, and then protocol addresses are for the logical tunnels. After all of that information, we see some client information entries at the bottom. And then there's, again, other parts of the NHRP message that we didn't really get into in a whole lot of detail because most of those fields are just defaulted to 0. Okay? With regard to spoke-to-spoke communication, when we get into DMVPN Phase 3, we'll take a look at some other captures like NHRP redirects, also NHRP queries where we're trying to reach a spoke destination. We're trying to establish a spoke-to-spoke tunnel because we're going to see different message types in that particular environment. All right. Other than that, it's really a basic protocol. There isn't a whole lot going on. There's really, in essence, only about 5 or 6 different packet types that you're going to see with NHRP altogether. And again, we'll take a look at some of those other ones in a little bit more detail later on. Okay. The registration request does tell us that we want to send packets to the tunnel interface, and we need to encapsulate them using those NBMA addresses. That's our overlay to underlay mapping. All right. On router 5, we could see that we had those different spokes are registered. And if I do a show IP NHRP and a show DMVPN on router 5, we will actually be able to show IP NHRP and show DMVPN. We can actually see that this router is registered as the hub. We actually see it listed right here, type hub. And that's based on the configuration. There's a flag field in the NHRP messages that identifies that router as the hub. All right, so we do the pings. We already did the pings. We took a look at how the pings are encapsulated. Pretty basic information, right? As far as the actual payload, it's just an IP packet becomes the payload of GRE instead of an NHRP datagram. All right, now IP routing hasn't been applied yet. All right, we're going to actually apply IP routing on the overlay, and then we'll see IP routing packets that are captured inside of or carried inside of GRE as well. It doesn't really matter from a functional standpoint, right? There's no way you could tell, in essence, from the configuration or from the packet captures that there's any difference between multi-point GRE and GRE. There's no indication in the packet headers themselves, certainly not in the GRE packet header, but in the NHRP messages, we don't see any indication of multicast or is supported, or we don't see any indication that this is a dynamic multi-point GRE interface as opposed to a static point-to-point GRE tunnel. The only difference that we see is in the parser config when we're going through the configuration in the command line parser. That's where you're going to see the difference. All right. Typically the source addresses are not going to be on the same common subnet as far as the MBMA addresses go. All right. Because we're doing phase 1 at this point, like I said, on the spoke routers, we specify the source and the destination. That NHRP map statement, let me pull that up real quick, based on the spoke configuration. This is kind of like a frame relay map command or an ATM map command where you're mapping it's slightly different because we're mapping in frame relay a local DELC to a remote IP, which can be dynamically created, but it's a similar concept, right? We're essentially trying to map one interface or one address to another address. Now, in the case of frame relay and ATM and even Ethernet, if we're doing MAC address to IP address bindings, it's layer 2 to layer 3. In this case, it's layer 3 to layer 3. That's the only significant difference because we're mapping a VPN interface to a NBMA interface. All right. So we're going to, in a little bit, we're going to enable routing over the network. We'll just start off by enabling RIP. And we're going to take a look at some of the considerations. And then in some of our future discussions, we're going to get into even more detail on what are some of the design considerations when it comes to doing multiple hubs for failover and redundancy and load balancing. And then also, what are some of the design considerations with some of the other routing protocols? That's definitely something that we want to take a look at. All right. We always enable whatever routing process we're going to enable over the tunnel interfaces. We do not enable them over the underlying network. So for example, if I wanted to come in here and I wanted to do some sort of, specify some sort of reachability, I could come into, actually let me do this on all three routers. Let's do this on router 1, router 2, and router 3. And I'm just going to do a config T IP route 0.0.0.0, 0.0.0.0, 10.10.10.5. All right. And what I'm doing is essentially I'm setting up a default route that points essentially all my default traffic to the tunnel interface on the hub. All right, now on router 5, I would have to identify some specific routes. So in the case of 192.168.20.0, 255.255.255.0, we're going to point that to 10.10.10.2. And then for 30.0, we'll point that to 3. And for 10.0, we'll point that to 1. These are all the loopbacks that exist which are essentially, in essence, our networks that exist behind each of these destinations. We don't want to route to the tunnel interface, right, directly. We want to route to the next hop, which is what routing is always going to be related to. If we were to route to the physical interface, that would bypass the operation of actually doing the tunnel encapsulation, because by sending the traffic to the tunnel interface, we know that we're going to encapsulate that information inside of GRE, and then we're going to send that over to the other tunnel destination. So I should be able to ping 192.168.10.1, and I'll source that from loopback 0. We should have some reachability. Let me make sure I got my addresses correct. Show IP interface brief. 192.168.10.1. Okay. Show IP route. Oh, we don't have our default route here. Show run pipe include IP route. It's pointing to 10.10.10.5. I may have to point it to the tunnel interface. Let me try that. Let's see. IP route 0.0.0.0, 0.0.0.0, tunnel 0. Oh, yeah, well, router 1's definitely not going to work. Remember, I shut that one down. So, of course, I got to remember that I shut it down. This one should work, though. So if I do a show IP interface brief, I had shut down router 1 because we were going to play with some of the other configurations on router 1. Let me go back to router 1 and let's turn on this guy and let's turn on this guy. Oops. If I could type show run IP route. All right. Well, we know reachability is going to be possible. You shouldn't have to point it to the tunnel interface. I mean, you could if you wanted to. It's probably best to point it to a next hop for, if we're doing resolutions for ARP and whatnot. It's going to be more efficient because, well, in the case of the spoke routers, it's not a big deal because they're point to point. So having a static route pointing to the tunnel interface on the spoke is okay. Because we're using a multi-point interface on the hub, you probably want to avoid sending routes out the tunnel interface because of the implications of ARP. It depends on what the physical interface is tied to is. In our case, it is Ethernet, so we want to kind of avoid having these massive ARP caches because we specified an exit interface instead of a destination. So destination IP. So let me go ahead and ping again 192.168.10.1, and we'll source that from loopback 0, and the ping goes through just fine, right? The point is here that you can do anything you want over the tunnel. You know, it could be BGP, could be EIGRP, could be static routing, OSPF, whatever. But you have to understand the implications of these various routing mechanisms if you're running those various routing mechanisms over these interfaces, because there are certain design considerations that you have to take into account. We'll definitely get into that as part of our lesson here, okay, and our future DMVPN lessons as well. All right. Now, as far as reachability goes, so if I'm pinging from, say, router 1, actually let's do a trace route. If I do a trace route to 192.168.20.1, so I'm going from spoke to spoke, we can see that that information goes to the .5 address, which is the tunnel interface on the hub, and then it goes down to the spoke. So all of this traffic that is passing from spoke to spoke has to go through the hub. Now, if I was running a distance vector routing protocol like RIP, which we're going to see at the end of our lesson here, or EIGRP, then split horizon could definitely be a problem, because we're tying the EIGRP process to the tunnel interface, which in turn is tied to the physical interface. But the issue we have is that with distance vector routing protocols, I'd never advertise routes out the same interface that I learned them on. So I might learn about the destination prefixes behind the spokes, and the spoke is going to learn, all the spokes are going to learn about the prefixes behind the hub, but one spoke is not going to learn another spoke's prefix because of that split horizon rule. That may actually be something that you want to go ahead and leave in, because maybe you don't want direct spoke-to-spoke communication. The next hop for the traffic, even if it's a dynamic process, is still going to be the hub, especially with DMVPN Phase 1. There's no mechanism in DMVPN for spokes to establish an adjacency with each other. So if I'm running EIGRP or OSPF, from a control plane perspective, it's still going to be a hub and spoke topology. There's no full mesh in this particular case. So from a control plane perspective, we're still running hub and spoke. Only the spokes can establish adjacencies with the hub router, but we can still create these dynamic spoke-to-spoke tunnels. All right? You may want to leave split horizon on, maybe for more efficiency, but there's going to be double encapsulation happening here, because the data is going to have to be encapsulated from the spoke to the hub. It's going to have to be de-encapsulated to be routed, and then it's going to have to be re-encapsulated down to the next spoke. I mean, for most modern DMVPN designs, Phase 1 is really obsolete, right? It's not going to be a version of DMVPN that we would typically run. I know, Tim, you mentioned that you guys are running DMVPN in your environment, DMVPN Phase 1 in your environment. But that could be because you just want to restrict the traffic flow from the spokes. Maybe you want to send it through some sort of traffic inspection engine, or some sort of traffic analysis engine at the hub. There's lots of reasons to justify only allowing a data plane and control plane hub and spoke environment. It just depends on what your environment is. Okay. Inside the GRE header, we do see the tunnel key. We saw the tunnel key. It's not encrypted, but the tunnel key is going to be used to separate basically that data plane by applying the tag in that data plane to distinguish the difference between traffic based on the tunnel key. So that tunnel key is really important in that particular case. The network ID that we have configured and the tunnel key, they're kind of optional. But if you have multiple clouds, tunnel clouds, you definitely want to have unique tunnel information identified. So the way we identify one tunnel cloud from the other is with the key ID or the network ID and the tunnel key. We can also do like ECMP between different tunnel clouds. We're actually going to take a look at that as one of our final DMVPN lessons, where we have multiple DMVPN hubs, and we're going to see how that configuration looks and see what some best practice standards are with regard to having multiple DMVPN clouds. All right. The hub may not be used for the data plane, but it's always going to be used for the control plane. In this case, it's used for both because we're running DMVPN Phase 1. All right. Now, if one of the things I'm going to demonstrate a little bit later is this idea that multicast traffic works over the DMVPN tunnel because it's simply encapsulated inside of a unicast datagram. We'll see that when we wrap up our lesson today. We're going to add our overlay routing protocol. In this case, it's going to be RIP version 2. And then our next lesson, we'll take a look at EIGRP and OSPF. We'll even take a look at some BGP stuff as well. Okay. All right. So let's do one more kind of review, if you will, of the differences between DMVPN Phase 1, Phase 2, and Phase 3, because that's something that we talked about in the last lesson, actually a couple lessons. But I just want to hit this up again because in our next lesson, after today's lesson, we're going to get into DMVPN Phase 2, and then we'll take a look at DMVPN Phase 3. Okay? It's not really from the perspective of how NHRP works or GRE works, because those are really some basic differences. There's only some basic differences between how NHRP and GRE works over these different phases. It's more from the perspective of what is the overall effect of this phase on our design, from a design perspective, from a routing perspective, from a protocol choice perspective, and so on. Obviously, we know that the difference is going to be spoke-to-spoke traffic patterns between Phase 1 and Phase 2 and Phase 3. The other major difference that you're going to see primarily between Phase 2 and Phase 3 is whether or not we can do things like summarization or some sort of default routing. So scalability becomes part of that discussion, right? If I want to scale my DMVPN network to 10,000 nodes or 20,000 nodes, DMVPN Phase 1 is probably not going to be my best choice. All right, but let's go ahead and break it down. DMVPN Phase 1 is still considered to be obsolete, even though it's still functional and we still run it. From a standard operational perspective, it is considered to be obsolete. We have a multi-point GRE interface on the hub, and then we have point-to-point GRE interfaces on the spokes. NHRP, as we saw from our demonstration, is still going to be required to allow the spokes to register to the hub, but there's no spoke-to-spoke tunnel, communication. All right. Routing is in Phase 1 there's some functionality that's available in Phase 1 and Phase 3 that doesn't exist in Phase 2, which is an interesting concept, right? Because you think as I move from one phase to the next, there's a progression of the features or the functionality that's going to be available kind of builds as I go into each phase. But the routing, from a routing perspective, in Phase 1, it's very similar to what we have in Phase 3. We can do summarization, we can do default routing. The next hop on the spokes is always going to be changed to the hub in this case, but there are limitations with the network types we can run. Specifically with OSPF, we have point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, non-broadcast multi-access, and so on. There's like five different network types that we have in OSPF. We'll get into that a little bit later on. Now, with regard to DMVPN Phase 2, which, by the way, is also considered to be obsolete. This is from Cisco's perspective. We run multi-point GRE on the hub, like before, but we also run multi-point GRE on the spoke routers as well. All right. Still need NHRP for spoke registration to the hub, but in addition to NHRP for the spoke registration to the hub, we also need NHRP for spoke-to-spoke resolution to be able to resolve spoke-to-spoke communication destinations. The spoke-to-spoke tunnel is always going to be triggered by the spoke, and that's going to be based on an on-demand service, meaning that we're only going to trigger spoke-to-spoke communication as needed, whereas the spoke-to-hub tunnels are going to be fixed and permanent based on the original registration. All right. From a routing perspective, we have some limitations on what we can do with DMVPN Phase 2. Summarization is not allowed in Phase 2. Default routing is not allowed in Phase 2. So I would say either you're going to choose to do Phase 1 or you're going to choose to do Phase 3. Most likely, you're never going to use Phase 2. You would choose to use Phase 1 if you wanted to restrict spoke-to-spoke communication, and you would use Phase 3 if you want to allow spoke-to-spoke communication with the ability to do scaling mechanisms like summarization and default routing. The next hop value does still need to be preserved by the hub, but that's where the NHRP redirect option, well, actually that's only available in Phase 3. So because the next hop address needs to be preserved by the hub, we have limitations as to what kind of summarization is allowed. I'm actually going to get into this. I'm going to demonstrate this when I go into my DMVPN Phase 2 configuration. And we're going to take a look at what some of the side effects are of running things like summarization in a DMVPN Phase 2 environment. You can get away with some summarization, right? But it's not very efficient. And I'll explain what I mean by that. There's this idea of multi-level hierarchy in DMVPN Phase 2 that's going to require some daisy chaining of traffic conditions. So I'll defer that discussion to when we get to our DMVPN Phase 2 lesson next time. All right. Now with Phase 3, pretty much the same as Phase 2. Spoke-to-spoke communication, multi-point GRE interfaces on both the hubs and the spokes. NHRP again is still going to be required for spoke registration to the hub, and NHRP is going to be required for spoke-to-spoke resolution. The only difference here, and this is the biggest difference, is when we receive an NHRP request, and if the hub recognizes that that NHRP message gets sent back out the same interface that it came in on, then we're going to do the NHRP redirect to identify to the spoke that it needs to update its routing table information. This is going to be an interesting discussion that we're going to see and demonstrate a little bit later on. So there's different types of routes now that are going to exist in our routing table based on those redirect messages that we're going to get from the hub. All right, this is why summarization and default routing is going to be supported in DMVPN Phase 3, specifically because of this NHRP redirect capability. All right, the destination is going to be reachable, but not through the hub. Initially, we might go through the hub to reach that destination, so we have that inefficient routing initially, but we're going to modify the routing information base to reflect the fact that we need to update our routing table so that we can send that traffic directly to the spoke. With regard to routing, summarization and default routing is going to be allowed in this case, and that's going to result in NHRP routes for those spoke-to-spoke tunnels. We'll see what those routes look like, how we can recognize the difference between our normal routing operations and our redirected routing operations in NHRP when we do our final DMVPN lesson, which is going to be for Phase 3. All right. The next hop is going to be changed depending on the destination. It's going to be from the hub IP to the spoke IP based on that NHRP redirect, whereas in DMVPN Phase 2, it's preserved. And certainly in DMVPN in Phase 1, it's definitely preserved because there's no spoke-to-spoke communication. All right. Because of the fact that the next hop on the spokes is always going to be changed by the hub based on the redirect, we need to make sure that the NHRP resolution process is going to be triggered by the hub itself to allow for that redirect. Because of this also, no daisy chaining with multi-level hierarchies is going to be required as well. Multi-level hierarchies are going to include things like OSPF, right, where we have a spine leaf spine design. All right. If we were to run OSPF, we do have some limitations, and this is why generally most people consider using EIGRP or BGP as the primary overlay protocol, because we have design limitations within OSPF as to where we can define summarization boundaries. We can only do summaries on area borders or area boundaries. So all the spokes basically would have to be in the same flooding domain and failure domain in order to facilitate that. And that makes the design really complex and not very efficient. We can't do any kind of summarization from the hub down to the spokes efficiently because of that requirement for the leaf spine leaf design. EIGRP and BGP, we talked about this many times. We're going to get into BGP quite a bit later on in one of our future sections. But with EIGRP and BGP, the topology, the hierarchy that we use is completely arbitrary. We can summarize at any point. We can manipulate path attributes and path selection processes at any point. So it makes it much more applicable to a DMVPN design. That's why, for the most part, you'll see, unless you're running OSPF as a flat domain, which can be done, right? That certainly takes out all the complexity of the spine leaf spine topology if you just simply run OSPF as a flat domain. Because I don't want to suggest, guys, that OSPF is not usable, right? It depends on how large the DMVPN network is scaling. So I'm not sure. I know, Tim, you mentioned you had saw some Cisco documentation referencing a dual DMVPN cloud design, but they were using OSPF. Most likely they were, and most likely they placed all the routers into one area in that particular case. All right. Yeah, go ahead.
Yeah, it wasn't phase one. There wasn't a static version that's what you'll see in the config. It's most likely a phase three, but I'm trying to be able to quickly ascertain the differences between it. Now I need to figure out what the difference between phase two and phase three is.
Right, which you're going to learn in our next lesson. So hopefully I'm
just trying to
solve this problem as quickly as possible. Absolutely. The configuration differences are very subtle. And that's where the challenge comes in with dealing with these different DMVPN phases, because there's not a significant difference in the configuration. Clearly the difference with phase one and the other phases is the idea that we're using multi-point GRE tunnels on the spokes. So you know if you're running a multi-point GRE configuration on the spoke, then you know that you're going to be running at least DMVPN Phase 2 or DMVPN Phase 3. I'll see if I can mention, I think there's a NHRP redirect command on the spokes, and that would indicate that you're running DMVPN Phase 3. So if you see some sort of NHRP redirect command, that will tell you that you're running DMVPN Phase 3. But again, it's a very subtle difference between Phase 2, Phase 3, and Phase 1. Do you see any kind of reference to DMVPN redirect or NHRP redirect?
I do not.
Okay. Yeah, on the spokes you would have a multi-point GRE interface, and you would have some sort of NHRP redirect command. So it's possible you're running DMVPN Phase 2, which has obviously its own limitations. So, but we'll, like I said, we'll get into those details in our next lesson, which will be probably on Saturday, and that should resolve some of your questions. I'll take a look at that configuration for you as well and see if I see anything glaringly obvious you know, I mean, this is something that's been running for some time, right? Or is this a brand new implementation?
It's been running for some time. They've had a problem back in December, and then a reboot seemed to fix it for a while. And but now, if you do a reboot, it just fixes it for maybe 20 minutes.
Interesting.
So Cisco recommended upgrading the iOS. So we did that, and now, well, we're going to be implementing that. That's what we're in the process of doing right now. But I thought the error messages were very strange. So I figured while we're doing that, I was going to look at the configuration to see if maybe something was kind of screwy. And anyway, that's kind of where we're at. So we'll be doing the dev tomorrow morning, and then Saturday we'll actually be doing the production environment.
Okay. Well, I think you had another problem similar to that where the iOS actually fixed the problem, right? Not
Other things that weren't like not VPN related.
Right, right.
That is, you know, like for instance QoS on the 5Ks.
Right.
Where we know we can't do QoS on the FEXs, we can only do COS, but attempting to put the configuration on actually killed the switches. Where it shouldn't have, it could have just ignored the config. So upgrading the iOS will fix that.
You guys always run into some interesting stuff happening over there. That's good though. That's how you learn this stuff, right? So.
Yeah, it's good training.
Yep. So anyway, I know we only have about 15 minutes left before Chris's bedtime, but we still got a little bit left to do here. Not too much, actually. We're getting close to the end here. We still have to do one more section. We're just going to kind of do our overlay routing. But basically, the design really just boils down to what you want the spokes to do, right? How do I want the spoke-to-spoke communication to happen? How do I want the routes to be controlled? And that's really the decision process when it comes to choosing one version of DMVPN over the other. In the CCIE lab, you're going to need to know all the variations. And that's why we talk about them. I'm not sure, you're certainly not going to have to implement multiple versions of DMVPN on the lab, but certainly on the written exam, you're going to have to understand the differences between the different types of DMVPN. And on the lab, you just don't know what you're going to be exposed to with regard to what they're going to be doing on the lab. All right, so we're more concerned about the routing design as opposed to the DMVPN design. That's really the biggest challenge when it comes to implementing DMVPN. BGP is always going to be the best option for large-scale deployments. EIGRP is probably going to be the best option for smaller-scale deployments. And with BGP, and we'll take a look at this as well in one of our future lessons, we can create things like BGP peer groups. The hub would be configured as a route reflector. We could summarize on the spokes and the hubs, but we need to know how the routes are deployed and understand the implications of having all of these different types of designs or routing designs. All right. So we've already done our DMVPN Phase 1 configuration. This is the last part of our lesson here. And we're going to take a look at initially just RIP routing, but we'll take a look at EIGRP, we'll take a look at OSPF, we'll take a look at BGP as we get into some of the other phases, and we'll look at that. I'm even going to show you guys a little bit about on-demand routing and how on-demand routing can be utilized over these DMVPN topologies as well. I mean, we know that in general, Phase 1 is considered to be obsolete, but we still need to talk about it. Summarization and default routing at the hub is allowed. The next hop on the spokes in this case is always going to be changed at the hub. And the hub is going to control the control plane, right? Now, the data plane in this particular case needs to pass through the hub as well because we are running a traditional hub and spoke environment. We can use the templates that we already created for the configuration. Keep in mind on the lab, exam, you are going to have access to the documentation, but DMVPN is not considered a routing technology. It's considered security and secure connectivity. So if you're looking for that, make sure you look there. Not all of the configuration options are going to be used in DMVPN Phase 1. We've already seen that. Router 5 in our topology is the hub. And again, we're not going to really add cryptography in this case. We're basically going to leave our configuration as it is. I just want to kind of add the routing piece on top of this to show you how it looks. All right. We want to make sure in our configuration that we have some sort of protection mechanism that allows us to protect what routers can join that DMVPN configuration. Now, ultimately, IPsec is going to protect us from rogue devices with the Phase 1 and Phase 2 encryption that IPsec provides, but we also add things like network ID and tunnel keys just to make sure that we're ensuring that the appropriate router is joining that DMVPN domain. And if we have multiple DMVPN clouds, we can identify which DMVPN cloud the traffic belongs to. All right, make sure you don't mix up that NHRP map command. We talked about that a lot in the last lesson where I kept referring to the NBMA address as the VPN address and vice versa. All right. Again, our spoke routers are just running a point-to-point tunnel, so we have to specify our source and destination tunnel interface. This is a traditional configuration. Let's go to our DMVPN configuration. This is a traditional configuration for DMVPN Phase 2, where we allow spoke-to-spoke communication, because this command right here is what sets up that MGRE interface. All right, and that's what you want to look for if you're trying to identify whether or not you're running DMVPN Phase 1 or Phase 2 or Phase 3. Okay. Now, if I was to do a debug, we can go ahead and do that. If I do a debug DMVPN on the hub, let's go over to the hub router here. Debug DMVPN. I think I need to do all. Let me try that. Debug DMVPN. Let's just do all. There we go. So I'm just going to capture. It's going to be pretty noisy, but I'm just going to capture all of the DMVPN information here. Let's do a config T, interface tunnel 0, shut, and no shut. All right. I should see some NHRP messages coming across the tunnel. There we go. Okay. So you can see it's a pretty robust output here. We're seeing just a bunch of messages being sent back and forth just based on the registration request through NHRP that we receive. But we can see in these messages here, we can see the mappings that are being created. So let me go back to the top here. Received a registration request on tunnel 0. It's IP, that's the address family, protocol 800. So this is all the stuff that we saw so this is essentially the NHRP header. The source NBMA address, and then also the source protocol and the destination protocol. So basically exactly what we were seeing in the Wireshark packet capture is what we're seeing in the DMVPN messages here. All right. This is the overlay and underlay mappings that we receive. NBMA is the underlay, and then the protocol information is the overlay. All right. Now, what I want to do is I just want to add, in this particular case, routing on top of this. And I want to see how routing is facilitated with this. But before we can do that, I've got to take out some of those static routes that I already specified because they have a lower administrative distance. So let me do come on, there we go. Show run pipe include IP route. And let's get rid of these static routes here. And we'll do the same thing. We'll get rid of those default routes that we have on our spoke routers as well. So let's do no IP route 10.10.10.5, and I'll just copy that and paste that into the other two routers here. Ah, dang it. All right. So what we want to do is we're going to go ahead and enable RIP routing. And I'm going to enable RIP routing on all the routers. So let's go ahead and select our routers here, including router 5. And let's do enable RIP here. Config T, router RIP, version 2. And we're going to do this on network 10.0.0.0. So that's going to enable a RIP on the tunnel interfaces. And then we also want to enable RIP on each of our loopbacks. I'm just going to copy these over. All right, we don't need all those network statements on all the routers, but that's okay. We're just going to paste this in, send this to all of the routers here. All right, let me just send a write to. So next time we get in here, I want to save that information. So I should be able to look at my routing table now, and I should see dynamic routes established in my routing table. Let's do a show IP route. And sure enough, we do have our RIP routes on our hub from each of the spokes. So notice the destination address is tunnel 0, or the destination interface is tunnel 0, exit interface, excuse me. And the destination IP address is the protocol address or the VPN address of the peer, 10.10.10.1 and 10.10.10.2 and so on. So I should be able to ping 192.168.20.1 from loopback 0, no problem. It's pretty simple, right? We're not running encryption, so we should be able to see in our packet captures as well a lot of the RIP messages that are going back and forth. We can see the RIP messages are multicast, but they're still carried inside of a unicast packet. So our underlay protocol, our transport protocol, is still unicast, even though we're carrying multicast traffic over that network, right? 224.0.0.9 is definitely multicast traffic. So we're not creating a multicast tunnel per se. The multicast traffic is just GRE encapsulated, okay? The spokes themselves are not able to form an adjacency with each other. Of course, in RIP, we don't really technically have adjacencies, but the spokes are not going to recognize each other as peers. Even if we're running EIGRP or OSPF, where we would have peering relationships between the spoke routers, or between the spoke and the hub, the spoke routers are never going to form an adjacency with each other. And this doesn't matter what phase of DMVPN you're running. In every phase, a multicast data plane, if you will, which would be required for spoke-to-spoke adjacencies, isn't supported. All right. The main point of the hub in any DMVPN deployment is to host the control plane functions, and for the routing protocols, and also the control plane functions for IPsec. Packets get routed at the data plane based on next hop addresses. And in the case of DMVPN Phase 3, that's going to be based on whatever NHRP resolution takes place. All right. If I ping from the loopbacks, I know that I can see those pings going through. If I do a trace route, in this case, it's going to look exactly like the trace route before. 192.168.20.1 source loopback 0. We can see What happened there? Trace route 192.168.20.1. Interesting. Show IP route. Oh, well, yeah, that would be such an idiot sometimes. Yeah, of course it's going to go directly to the spoke from the hub. See, these are the kind of things you guys should be catching me on, man. I'm doing a trace route from the hub to the spoke, and I'm thinking, there's only one hop. There's only one hop. Why is it only one hop? Because there's only one hop from the hub to the spoke. Let's try that again. Trace route 192.168.20.1 source loopback 0. And obviously you guys understand what's going to happen in this particular case. We should see ping 192.168.20.1 source loopback 0. Interesting. Show IP. Our tunnels are up. Oh, never mind. We know why that's happening. I know why that's happening. We're running RIP, right? RIP is a distance vector routing protocol. So the issue that we're running in here is a split horizon issue. If I look at the routing table on router 1, show IP route, I can get, I'll be able to see the prefix from the hub, .50, but I can't see the prefixes of .20 and .30 from the spokes because of split horizon. All right. So we can fix that problem by simply going into the tunnel interface, no IP split horizon, and that should, yeah, no IP split horizon applies to RIP by default. Now if I do a show IP route, eventually we have to wait our 30 seconds until we get the update, but eventually I should learn about the 20 subnet and the 30 subnet because split horizon is now disabled on the tunnel interface on the hub. There we go. So now if I do my trace route, 20.1 source loopback 0, there we go. Traffic goes to the hub and then goes over to router 2. Right? Normal operations, what we would expect to see in a traditional hub and spoke DMVPN Phase 1 topology. All right. Now, there may be reasons why we want to limit the amount of information that the spokes get, especially for running DMVPN Phase 1. There's really no reason that the spokes themselves need to receive anything from any routes from the hub, right? All we need essentially is some sort of default route. All right, so we can do a couple of, we can do like a default information originate on the hub and then send that into the tunnel if we want. Let me go ahead and we could disable split horizon like I said, but remember our overall design, our goal of our design is to limit or minimize the control plane load. In any kind of routing implementation, we're always trying to minimize the control plane mode, but still have the capability of doing dynamic routing, efficient routing, and so on. So in the case of DMVPN Phase 1, it makes sense to only send a default route to those spokes. So we can do that actually this way. I still want to be able to learn the prefixes from the hub. Excuse me. I still want to learn the prefixes on the hub from the spokes, but I only want to send a default route to the spoke routers. So on the hub, I could do something like some sort of filtering function. I could do IP prefix list. We'll just call it default. And I'm just going to permit quad 0/0. And then I'm going to go into router RIP. And I'm going to do a distribute list. Distribute list prefix default. And out of tunnel 0. So I'm applying this prefix list to filter the routes that I'm sending out of tunnel 0, and then on router 1, router 2, and router 3, I should only see that default route. I'm not seeing the default route at all. Yeah, I forget that RIP is really slow, so we have to wait our time here. But eventually what should happen is I should see that I'm getting just a gateway of last resort, and those other prefixes are not going to be advertised out of the tunnel interface based on the prefix list that I applied to the RIP process. All right. There may be some hold down timers that are involved as well, but I should already be getting a default route. Let me check my configuration here. Default, prefix list default, out tunnel 0. Do show run section RIP. Distribute list prefix default, out tunnel 0. Do show section prefix. Permit 0. So when we do an exact match, you know what? I don't think it's being sent out because we're not originating the route. So let's do a default information originate on the router as well, because we're not generating a default route. There we go. Now those other routes are in a hold down state. Eventually those should go away. Let me do a show IP route 192.168.20.0. Show RIP database. Show IP RIP database. And I should see if those guys are I wonder why it's not filtering out those routes. There we go. They were probably in a hold down state. But you can see I still have the default route, right? So I still have reachability to the other destinations if I do a trace route to 192.168.20.1 source loopback 0. I can still reach that destination. So, so that's and that's kind of what our goal is, right? I mean, we try to the data plane is going to go through the hub anyway. So it doesn't really matter if we're getting specific routing information from the hub for the other prefixes that exist behind the spokes. All right. Also, if you don't specify, just one last thing I want to mention. You know how we identified that router 5 was the hub? In the configuration, we assume that we're the hub if we don't have a next hop server specified. So here, we have the IP NHRP next hop server command, which indicates that we're telling this router who the hub is. So if you look at the hub configuration, there is no next hop server specified. So we make the assumption that router 5 is the hub in this particular case. All right. So that completes our discussion about the different phases, about DMVPN Phase 1. We're going to go ahead and end this lesson. And let me see what we're going to do for the next lesson, probably on Saturday, so we can maintain our 3 lessons a week. All right, give me 1 second.